Hello everyone. So today we're going to go over section 7.4, characteristics of logarithmic function with base 10 and base e. So in order to understand what a logarithmic function is, we have to understand what a logarithm is first. Um, but before we talk about that, the logarithmic functions that we'll be looking at are of a certain form. They will be of the form y equals a times log base b of x, where a is not 0, b is greater than 0, and b is not 1. So what is a logarithm? Suppose you have the exponential relationship that we had before, y equals b to the x power. Okay, so if you are to write this expression using logarithms, it will look like this. It will be log base b of y is equal to x. And it will be a little bit easier to substitute some numbers for this to make sense. So let's say, for example, we can have something like 100 is equal to 10 squared. Okay, that is an equation written in exponential form. 10 squared has the 2 here is an exponent. 10 is the base, of course, and 10 squared is 100. So if we were to write this using a logarithm, then we have log base 10 of 100 is equal to 2. So one way to think about the logarithm is to say, well, if this is our argument, which is what it's called, and the base here, this is base 10, and the 2 is the value. Oops. Okay, so if we have an argument of 100 and the base is 10, we're saying, well, 10 to what power is equal to 100, and the value is 2. So it's related to the exponential function. And that's why a lot of the same restrictions will apply. So think about this right here. Right, we have a very similar restriction for the base of exponential functions that we talked about before. And a is not going to be 0 because if a were 0, then this whole thing just becomes 0 and you don't have much of a function. Okay, so let's look at our first logarithmic function. We have f of x equals to log base 10 of x. We're going to use the table of values to determine what the values are. So we'll begin with log base 10 of -1. Now, if you ever see a logarithm where the base is not written, then the base is assumed to be 10. Base 10 is known as the common logarithm for that reason. All right, so if you think about it, what you're asking really is 10 to the what power is equal to -1. Now, from the exponential function, you will notice that there's no power of 10 that's negative. So this is actually undefined. Okay, and you can also use a calculator to find that out. We have -1, and then logarithm is as invalid input, so it is undefined. Same thing with log 0. There's no power of 10 that's 0 because the exponential function has no x-intercept, so we know that to be the case. And that's also undefined. Okay, what about 1? So let's say we have 1. The logarithm of 1 would be 0. Again, 10 to the what power is equal to 1. Well, 10 to the 0 power is equal to 1, so that's why the value is 0. And then the rest of these are just going to be calculator values the rest of the way, because none of these are powers of 10, right? So it's not going to be like a whole number. So 2, log base 10 of 2 is 0.301. And again, the rest of these are just going to be calculated values. Um, and you can see that they are approaching 1. So by the time you get to log base 10 of 10, you get 1. 0.602 and 0.699. All right, so if you were to graph this, you will get a graph that looks like this. Okay. So if the argument is between 0 and 1, then your logarithm is going to be negative. And then once you have 1, then the logarithm is 0, and then it becomes positive and increases slowly. Kind of like this. Okay, it might remind you of a graph, and if it does, that's good. If it doesn't, that's okay. So I'm just gonna go ahead and draw this diagonal here. Um, this is the line y equals x. And the logarithmic function is an inverse of the exponential function with the corresponding base. So in this case, if I were to sketch y equals 10 to the x power, I'll get a mirror image off of the line y equals x. So this would be y equals 10 to the x power, and the function that we graphed in orange is y equals log base 10 of x. Okay, so one of the reasons why we use logarithm is that it linearizes an exponential relationship. So you can see that in a typical exponential function, the one in purple, the y value increases really fast. But we often don't want that. We want to look at a straight line, so that's why we use logarithmic scales when we're dealing with exponential functions. Okay. So some properties of the orange graph now then. It has no y-intercept, just as how the exponential function has no x-intercept. The logarithmic function will have no y-intercepts. Its x-intercept is 1. That should also be familiar. The domain x is greater than 0. Range y is element of the real numbers. The end behavior, notice that it doesn't cross into where x is negative. So the end behavior is actually quadrant 4 to quadrant 1, and is increasing. Okay, so what happens if you have a different value of a? So in this first example, our a value is equal to 1. Okay, so let's quickly go over that. In example 2, we have g of x is equal to 2 times log base 10 of x, so very similar. So essentially everything is going to be multiplied by 2. So the first two values here are still going to be undefined. That doesn't change. Okay, and then notice that in the one spot here, log base 10 of 1 is still 0, and then we have 2 times 0, which is again just 0. And then the rest of the value will be double what they were before because of the 2 in front of the logarithm. So just going to go ahead and write those down. We have 0.602 and then 0.954, 1.204, and 1.398. And the graph will look very similar to the last one. It will be vertically stretched by a factor of 2, so it will be increasing faster, as in it will be more like this. But very similar to before. The x-intercept is still 1, 0. Okay, so if we were to go ahead and record all this, number of y-intercept, still none, just like before. The x-intercept is still 1, just like before. So notice that the a value doesn't change the x-intercept. In the exponential functions, the a value changed the y-intercept, but in the logarithmic function, the a value doesn't change the x-intercept. It's very important to remember that. The domain is still x is greater than 0. Range is the same before as well. And the end behavior also just like before, 4 to 1, and is increasing. Alrighty. So in the original version of this, I made almost too many examples. We're going to skip a few of them. This one is very similar. Example C is just instead of a 2 as your a value, you have 5, so it's not too big of a difference. Let's move on to example D. Notice how this time the a value is negative. So how does that work? Well, the first two x values, the -1 and the 0, they are still going to lead to the function being undefined, because that has more to do with the logarithm than the a value. And again, log base 10 of 1 is still 0, -5 times 0 is still 0, so that doesn't change either. But as you can kind of imagine, because of the negative negative coefficient of -5, the rest of these values here will be negative. And if you use a calculator, you'll get -1.505, -2.386, -3.010, and -3.495. All right, so if you were to graph this, then it will be actually the same graph but upside down. Again, it will decrease faster than the previous two graphs because the a value is, well, 5 is greater than 2. So again, the x-intercept is still 1, 0. So if you think about the properties here, there's still no y-intercepts. There's still one x-intercept. The domain is still x is greater than 0. The range is still y is an element of the real numbers. And the end behavior now is going to be 1 to 4. And it's going to be decreasing. So that is what the a value really changes and how it really matters here. Okay, just as how we were able to produce decreasing and increasing exponential functions, we have now a way to produce increasing and decreasing logarithmic functions. And there is a difference between the two. Okay, so quick note here. In the title, it says logarithms of base 10 and base e. Logarithm of base 10 usually are just written as log with no base. And then sometimes you will see this ln notation, which is the logarithm in terms of base e. E is a irrational number that has a bunch of different applications. We'll talk more about that in future examples, but we'll leave that discussion for a bit later. Okay. All right, so if we are to continue, okay, so here we are going to be given some functions. We just want to predict the x-intercept, the number of y-intercept, the end behavior, domain, and range. So in this case, we're just going to be looking at the a and b values, just like what we did with the exponential function. The a value is 15, and the b value is 10. Okay, so this is going to be an increasing logarithmic functions. So it has a graph that looks like this. Okay, that's not the best sketch. A little bit better. Okay, that's better. Okay, so the x-intercept is still going to be 1, 0. There will be no y-intercept. Okay, the end behavior, this is an increasing function. So it will be from 4 to 1, increasing. The domain is going to be x is greater than 0. And the range is just like the other logarithmic function once again. Okay, so again, same thing here, except for the a value this time around is negative, and the base is e. Okay, so we're going to have an upside down logarithmic function, something that looks like this. And the properties will pretty much be the same. The only change really is the end behavior. Instead of 4 to 1, it will be 1 to 4. Okay. So domain is greater than 0. Sorry, x is greater than 0. Range, y is an element of the real numbers, as usual. Again, I made too many examples from before, so we're going to skip over the next couple and just go to the last part, which is the matching part. But it would be easier if these were, let's say, Roman numerals instead. There we go. All right, so we're going to be matching graphs here. You'll notice that because there's only really two different shapes for the logarithmic function, that I've included some exponential functions here, so we can tell the difference between the two. Graph A is a function that's only in quadrants 1 and 4 and is decreasing. So this would be a negative log function. So this would be function 4. Graph B, as you can see, is coming from quadrant 2 into quadrant 1. It's increasing. So this will be graph 1, sorry, function 1. Okay, this is an increasing exponential function. Last couple here we have graph C is an increasing log function, so this will be function number 3, positive log function. Positive as in the a value is going to be positive. That's what that means. And finally, graph D will be function 2. It is a decreasing exponential function. Okay, so today, quite a lot of topics that were covered today. First was the introduction of what a logarithmic, sorry, logarithm is, and then we talk about logarithmic functions, the very basic types, with just an a value and then the base being the b value, whether they are positive or negative, some of the characteristics that they may have, and then a comparison between the different functions and what graphs they can produce. Okay, so that's it for today. Thank you for listening.